Okay, so we're going to derive the equations of motion for constant or uniform acceleration. So let's first remind ourselves what we mean by uniform or constant acceleration. I can tell you what we don't mean. We don't mean constant velocity. Constant velocity means you have the same velocity the whole time, 50 miles an hour for 3 hours. You know you're going to go 150 miles, and we don't need fancy equations to help us do that. But constant acceleration is different. Constant acceleration is the very specific case where your velocity is changing, but it's changing uniformly. It's going up or it's going down by the same amount every second. So a case that would not apply to that would not be described by constant acceleration would be something like this. If you have a velocity versus time graph and it's like that, that's not constant acceleration. The velocity is changing by different amounts every second. So we are concerning ourselves right now only with linear velocity graphs. Linear velocity graphs where I start at some initial velocity, I wind up at some final velocity, and the change in between is a nice steady line. In that case, my acceleration can be given by just the straight slope of that graph, the change in velocity divided by time. So take a minute and convince yourself that about what uniform constant acceleration is and what it is not. It's not constant velocity. Constant velocity would look like this. Your velocity is the same the whole time. We're not dealing with that situation. And it's not wacky velocity where it's changing in all different kinds of ways. It's a linear, steady velocity. And this is going to be a very important assumption that underlies everything that we do. Okay, so first we want to figure out, there's a few key equations that physicists use to describe uniform constant acceleration. And it answers the questions, how far, how fast, how long does it take? But under this slightly more complicated situation where you're covering a different amount of distance in every second, and so you need more than just rate times time is distance to answer the questions of where you are and how long it's going to take you to get somewhere. All right. So I'm going to redraw my little graph. It doesn't matter if your velocity is increasing or decreasing. It doesn't matter if it's positive or negative, but I'm just going to keep it simple, a nice intuitive, steady increase in velocity, starting at some number, ending at some number. And like I said earlier, my acceleration is just the slope of that graph. And since it's a linear line, it has a steady slope. And that's the definition of my uniform acceleration. The acceleration is a number because the slope of this graph is not changing. It's a number. This is actually my first equation of motion for constant acceleration, although it's often rewritten by multiplying both sides by t and then solving for v final. So you can rewrite this as TA equals V final minus V initial, and then one more step would just be V final equals V initial plus AT. My final velocity equals my initial velocity plus the product of my acceleration and time. So this is actually our first equation of motion. Let's look at our second equation of motion. It's really just a matter of taking what we know and reconfiguring it so that we have different variables depending upon the needs of the problem we're trying to solve. So coming back to that assumption of constant acceleration, the only way right now that we really know how to calculate distance is using our good old-fashioned equation, average velocity times time is displacement. That's actually going to be the foundation for all of the equations of motion for constant acceleration. Average velocity times time is displacement, or we've written that also as average velocity is displacement divided by time. If your acceleration is constant, let's talk about what that average velocity is. With a nice linear uniform increase in velocity, it means that your average velocity is actually going to fall right in between your initial and final velocities. Now, that would not be the case if you had some squiggly velocity. The average velocity could really lie anywhere on the line depending on the shape of the line. But with a nice straight linear velocity, your average velocity will always just be a straight, traditional halfway point between the initial and the final. It will just be given by a straight mathematical average. Taking that, I can actually now use that with this equation over here. Instead of V average, I'm going to put V initial plus V final over 2, which is only true for uniform acceleration. That's where my assumption is coming in. It comes in right over there, times time is my displacement, my change in position. Now I could that's going to actually be a useful like intermediate point, but we don't ever really write that as an equation. What we typically do is we think about what variables might we not care about or might not know. And so we're going to start with trying to eliminate final velocity from this equation, because sometimes you really just don't care how fast you're going at the end and you want to know other stuff. And the way we're going to do that is we're going to take the final velocity from equation 1 and we're going to plug it in for the final velocity in this little intermediate equation here. So I'm going to do that right now. V initial plus V final, but for V final I'm putting in equation 1, V initial So that's V initial plus V final. This is just V final divided by 2. That whole thing times time equals X final minus X initial. Okay, that looks a little messy, but it's really not that bad. I'm going to go on to the next slide. I'm going to rewrite it, and then we'll see what it's going to give us, which is pretty cool. So remember, I was starting with V initial plus V final over 2, average velocity, times time is displacement. I substituted in for V final. V initial plus AT from the other equation. That whole thing divided by 2 times time is X final minus X initial. And now I'm just going to expand it all out and do my algebra. So first I'm going to deal with what's in these big parentheses. I have V initial plus V initial plus AT over 2 times T equals X final minus X initial. And then one more step, 2V initial plus AT over 2 times T equals X final minus X initial. And then I'm going to bring my T in here, and I'm going to cancel out my 2's, and I get V initial T plus AT squared over 2 equals X final minus X initial. And this is often written as a final form. X final equals X initial plus V initial T plus 1/2 AT squared. You'll notice we've eliminated the final velocity from this equation. And so if we just want to know how far you've gone, if you know where you've started, how fast you're going initially, your acceleration, and how much time you have, this equation is going to help you figure it out. Okay, so we have two of our big three right now. We have our first equation, v final equals v initial plus at. Our second equation, x final equals x initial plus v initial t plus 1/2 at squared. And now we want a third equation. And the third equation that we want is one that doesn't have information about time. The most efficient way to get that one is to not use these guys, but to go back well, we're going to use one of them, but we're going to go back to that intermediate equation again, that the average velocity times time is equal to displacement. So I'm going to write that out. We're going to start here. Average velocity, v initial plus v final over 2, that was your average velocity if you remember, times time is your displacement. Now, I have another little equation up here that I can rewrite in terms of time. So I can solve that for time. And if I rewrite this little guy here, I get v final minus v initial over a equals t. Same equation, v final minus v initial is at. But what I can do is I can now substitute that in for time in this equation. And I get v initial plus v final over 2 times v final minus v initial over a equals x final minus x initial. So I'm going to do a couple more little things. I'm going to multiply both sides by 2a. So that'll get rid of that in the basement. And I get v initial plus v final times v final minus v initial equals x final minus x initial times 2a. And now, if you remember your foils, I could do my little foil over here to try to expand out those parentheses. And if you do that algebra, you wind up with v final squared minus v initial squared equals x final minus x initial times 2a. And this equation is normally written out as v final squared equals v initial squared plus 2a x final minus x initial. This is equation number 3 of our big three. So I'm going to write them all out on the next slide. 1. V final equals V initial plus AT. This one has no position information. 2. X final equals X initial plus V initial t plus 1/2 AT squared. This one has no information about V final, so if you don't care about your final speed or you don't know it, that's a very good equation to use. And then there's number 3, which is V final squared equals V initial squared plus 2a x final minus x initial. And this one has no information about time. And then I will write, it's sort of a parentheses for the definition of average velocity. Average velocity times time equals displacement, which is also equal to the average velocity written out this way. That was our intermediate equation. We really don't use that one that often, but it can come in handy every now and then. So I'll leave it there. But these guys are our big three equations for motion at a constant acceleration. And remember, they're only true if I have a velocity versus time graph that is linear in one way or another. So the velocity has to be changing in a uniform linear way. If that's the case, then I can write my average velocity as a straight average of the initial and final velocities, and then and that allows me to derive equations 1, 2, and 3. Next video, we'll do a couple of really quick examples, but I'll pause it here so that you can take a break and process all of it.